Welcome to INL's first Research SLAM. So just really quickly, across the lab complex, the early career professionals are doing a similar thing as we're doing here today, where the researchers are presenting their research to audiences with the thought, how would I present my ideas to an audience that doesn't have a scientific background? It's kind of a unique approach to the work that we traditionally do here at the laboratory. But I think it's one that's important when we're thinking about how we can get buy-in from our community and in government agencies and the awesome work that we do here at the laboratory. So thank you for being our guinea pigs this year. I'm J.R. Ratliff with National University Programs. I help Lisa Scott and I help run the postdoc office here. And so the early career postdocs fall into that category. And so we are spearheading the activities today. But I want to give a special thanks to Jessica Dixon, who's not here. She really sort of got the ball rolling with this event. And so if you see her, make sure you tell her thanks. We're going to get started here so we can give the contestants some relief because they're sitting over there. So again, welcome. And we really value you being here. We know that you all are very busy, and so we're thankful that you're here. So just want to briefly talk about we had sponsors from across the lab that gave us these awesome, not the checks, the paper checks, but real money. So we have $3,000 for our first place winner. And for our second place, we have $1,500. And then the People's Choice Award, which we'll explain a little bit later, is $750. The most important thing, I want to remind the contestants who win, remember who invited you to do this. Just kidding. We'd like to thank our judges. So Nicole, Chandu, Richard, and Corey, thank you so much for being here. Nicole and Corey are with our science communications team. Rich is with the analytical laboratory, and Chandu is with the advanced reactor technology design team. So we have a good bunch of judges here who are going to be looking at these presentations from a few points of view. One is, remember, the focus of this competition is we really want to make sure the science is right. And so we have our colleagues here who can help to make sure that that the presenters are representing the science in an effective way. And we also have our colleagues from communication strategies. Again, remember, a lot of the thought is how do we share these ideas with folks who don't have the backgrounds that many of you have? And so we have our colleagues who've been in science communications to make sure that's done well. And so that's pretty much our judging scheme for today. All right, so without further ado, we're going to start with Vasilios, computational scientist from Computational Framework C510. Welcome, Vasilios.
Thank you, Kasim. That's me. Hello, everybody. I'm so happy to be here. Thank you for your introduction. I'm Vasilios Kyriakopoulos. I'm a computational scientist. I came from Greece to work here. And as many of you, I started doing nuclear engineering because it sounds so cool. Little did I know that most of it has to do with just boiling water. So here is the kettle over there. But it's a bit more complicated than that. So in a nuclear reactor, we want to boil some water or in general, heat some sort of fluid. So we have these big complicated machines that heat a fluid and then that energy is transferred to a secondary loop and that creates steam and the steam turns a power generator. It's very important for us to know the distribution of temperature in the fluid. So in the reactor, we have assemblies such as this. wire-wrapped. This is a wire-wrapped fuel assembly for sodium-cooled reactors, and this is the cooler rim. And there are many flavors on the analysis of the fluid, depending on their fidelity. So here we have the picture of the horse. DNS is the highest form of CFD, and it's very computationally inexpensive. System codes are usually one-dimensional codes that are used for the balance of plant analysis, and somewhere in between are the subchannel codes, which is what I work on. So the subchannel codes solve the subchannel equations, which are equations of conservation of mass, energy, and momentum. And they are produced by integrating those equations over the subchannel volumes. So the subchannel volumes, as you can see here, are much larger than the ones that we have for CFD. So that makes for less computational effort, but they're also non-one-dimensional. It's a 3D computation, so it offers more fidelity than system codes. So we can have square subchannels or triangular subchannels. In this case, we can see triangular subchannels. And the subchannel equations are derived by integrating the conservation equations of mass, momentum, and energy over these volumes. And my job as a computational scientist is to find the correct way and the algorithms and discretize these equations and then code it all up in MOOS, which is INL's multiphysics object-oriented framework. And that's basically what I do, and that's what I came here to present to you.
All right, so our next presenter will be Vaclav, Model and Simulation Engineer for Integrated Energies and Market Analysis. He's C170. Welcome, Vaclav.
So, hello everyone. I believe that the need for storing electricity in future grids full of wind and solar, and perhaps steady nuclear, is quite well understood. But there's a catch. According to some predictions, even more than 90% of all electricity that will need to be stored will require charging or discharging durations between 4 or 5 hours and about 1 week. So in this period, let's say for our duration of storage, it's upper limit of lithium batteries. Then we can also, of course, use hydrogen. But electrolyzers are quite expensive. They are good for smaller systems, slowly building up your supplies of hydrogen over maybe a week, maybe between seasons. And having high capacity of batteries or large electrolyzers is just too expensive. But I have a solution for you. We can convert the electricity to heat, store the heat, or in any form as hot or cold, and then convert it back to power. As it involves thermodynamic conversions, so these systems are named after the pioneer of engineering thermodynamics, Nicolas Sadi-Carnot. Then why would we use this? Why would we store electricity in this way? It's cheap. We can use molten salts, we can use special oils, and we can basically use just piled up hot rocks, gravel, dirt, and that is cheap. Now, also you can build these systems basically anywhere you want. Not like pumped hydro. You don't use expensive and toxic materials, and I could go on with the benefits for a long time. There are several types of these systems. Some of them, to make the heat, use systems like a little bit similar to aircon or heat pumps. They are a bit more expensive, have a bit higher efficiency. Or, as you can see here, we can take advantage of existing infrastructure, such as coal plants. Instead of shutting them down, just build thermal energy storage and electric heater right next to it. Very cheap system. And suddenly, from dirty coal plant, you get electricity storage system supporting renewables, supporting net zero future. So, you might say that such system might be not very efficient. Yeah, it can have maybe 40% of efficiency. It's not too high. But consider the shift of paradigm with having more and more common negative electricity prices. Do you then need to care that much about the efficiency? And now, when these systems are so great, why doesn't everybody use it yet? Well, the devil is in the detail, and my research is making sure that everything will work together smoothly and nicely, as I have tried to explain to you in this presentation. And when it does, we will get almost literally dirt cheap method of storing electricity. Thank you.
So our next presenter is Asif. Asif is a postdoctoral research associate in biological processing, the materials recycling and recovery, B622. Welcome, Asif. Come on.
All of you must be carrying a cell phone today with you. Did you know that our cell phones contain 5 different types of rare earth elements, in short REE, in their magnets and speakers? So similarly, electric cars, MRI machines, solar panels, and even waste from mining industries contain different forms of REE. So what are these REE? These are the elements from the lanthanide series in the periodic table. US imported around $200 million worth of these metals last year. So why are they so rare? Because their recovery from waste is a complex process. Usually they are found in a mix with other metals, and also they are very stable at their trivalent form, so do not get reduced very easily. Chemical and electrochemical processes are the main one for their recovery in current practice, but they generate hazardous waste, and also the end product is usually a mix of different REE. So if we can tie biological reduction to these processes, they can offer cheaper, more selective, and environment-friendly solutions to the recovery of REE. Now, this is where my research can play a significant role. At INL, we are exploring different forms of REE reduction using microorganisms. My brain is so occupied with microbes that when I saw the term SLAM, I thought about my anaerobic bugs immediately and decided to give them a better name for the service, which is SLAM. It stands for Selective Lanthanides Accepting Microorganisms. Let me tell you why. Think about us humans. We take oxygen that acts as electron acceptor in our body to break sugar and give us energy. Similarly, anaerobic bacteria can take metals as electron acceptors, reduce them, and use that reaction energy for their growth. We wanted to use the same phenomenon to see if some well-known metal reducers can actually reduce stable RE or not. And guess what? We actually found one of our bugs is reducing specific REE in our lab. And right now we are trying to quantify their building blocks or proteins to find out the underlying mechanism. So there you go. Like we have like SLAM actually is preferable for selective recovery of REE. So guys, stay tuned, and hopefully you will hear more exciting news about my SLAM in coming days. Thank you.
Ella Peck, who is a postdoctoral research associate in condensed matter and material physics, B615. Ella, welcome.
Thank you for the introduction. Yeah, my name is Ella Peck, and thank you again also for coming to this SLAM. So I'll start with explaining how nuclear power plant works. The simplified version is this. You have a rod, which is this one, which is the nuclear fuel. You put it inside the water tank, and then it boils the water, creates steam, and the steam drives the turbine. What we will focus on is the nuclear fuel. Because like in this chain reaction, it ended up creating some defects or damaging the sample. And this blocks the heat from transferring properly. And we want to make the nuclear fuel to be more efficient in transferring this heat. So one way is by introducing interfaces. Previous studies have observed that these defects ended up going into the interfaces getting annihilated or segregated. In a way, you can imagine this scenario. You are in a grocery store, and then you have a cleaning machine. It's trying to clean the aisles, which is these red lines, the energy trying to get transferred. But you have people here and there with their carts blocking the aisles, which is the defects here. Because of that, the cleaning machine, of course, cannot go through. But if you have sample stand, for example, sample stand represents the interface. The people ended up going to the sample stands, clearing the aisles of people, and the cleaning machines can freely clean the aisles now. The same way with interfaces. You can now have the energy go through because like the defects ended up going to the interface. However, if there are already too many people in the sample stand, then people wouldn't be attracted as much to go to the sample stand. The same way with interface. If you have too many defects in the interface, then more likely the defects cannot go into the interface anymore. So we grow our samples using molecular beam epitaxy, where we can grow sample with interfaces with minimal defects. In order to really observe if interface really help with defects, we shine laser to our sample. Nothing happens with the regular sample, but for the sample with interfaces, over time the thermal conductivity increases, which means that the ability to transfer heat is getting better. And our study is trying to observe what's causing these defects to get healed. Is it the heat from the laser, or is it the photon from the laser? In addition to that, we are trying to observe what's the optimum distance between the interface so that the defects can still see the interface and go to there. Just like if the sample stand is too far away, you cannot really see it and you cannot go there. So yeah, that's a summary of my study. Hope it helps the future nuclear fuel. Thank you.
Participant will be Kevin Vallejo, who is a staff scientist in the condensed matter and material physics, B15. Let's welcome Kevin to the stage.
The ACs have been working a lot harder lately, haven't they? The extent of ice in the Antarctic Sea is at a record low, according to NOAA. And there's cities in Arizona that don't go below 90 degrees even at night for months. It seems like our planet is experiencing a climate crisis. And in order to solve this crisis, it looks like nuclear energy is coming at the forefront as a solution. However, it is not very easy. We need to understand the fundamental processes of materials and physics that are happening for nuclear to be a viable solution. At the heart of these problems is uranium. Uranium is giving us problems because the configuration of its electrons is complex. Why? Well, because there's so many of them. How do they even arrange themselves? This is the heaviest naturally occurring element in the universe. If we do not understand how the electrons are arranged in the uranium, how are we going to put them in a compound? How are we going to put it in a fuel? How are we going to make sure that our reactors are operating safely? This is why we need to understand what is uranium doing in the complexes, in the materials, so that we can put them in the reactor, so that we don't have to extend the problem, we don't have to extend the crisis, we don't have to extend the time, we get the solution. This is where my research comes in. My research focuses on getting the best spray paint can that money can buy you. It's called molecular beam epitaxy. You grab these very clean elements, you put them in a tiny oven, and then you start spraying thin films of these atoms. Why do we want to do this? Well, because we want to put the elements in the places they're supposed to go. There are amazing industrial techniques out there making the fuels that reactors need right now. They make them in tiny marbles, they make them in tiny pellets, they make them in huge rods. However, there are imperfections, there are impurities, there are things incorporated into these fuels that make our understanding a little bit more complicated because of the complex mathematical modeling we need to understand how the physical properties are happening. So if you have your fuel, you need to figure out how is the heat moving around? How is the water affecting it? How are all these extra atoms making my fuel not perform at its best? That is why the Idaho National Laboratory is uniquely positioned to understand the uranium complexes using this magnificent spray paint can by creating the films and the samples with high quality needed to not only understand the field that will go into the reactor, not pictured, but also to understand the fundamental physics that goes in here. How are we doing this? Each one of these atoms is correctly positioned, is near the correct neighbors, is away from any imperfections. This way, we can see how it wants to behave naturally. It's like if you put your uncle and your aunt in the right situation, that's when they want to behave. Looking at nuclear physics from the right position not only helps us tackle this problem, it also helps us take a peek at the cosmos. Thank you.
Michael Moorhead is our next contestant. Michael is an advanced nuclear materials scientist in irradiated fusion materials, C610. Let's welcome Michael to the stage.
So, thank you, JR. My name is Michael Moorhead, and today my goal is to convince everyone that metallurgy is like baking a cake. And the reason that is because when you go to bake a cake, the first thing you do is you go to your pantry, and regardless of what kind of cake you're baking, you look for the same sort of ingredients: your flour, eggs, water, oil, chocolate, and you mix these all together and you heat them up. And at the end of the day, hopefully, if you got the ratios right, you have something that you can eat. Now, when it comes to metallurgy, rather than going to the pantry, the first thing that we do is we instead go to the periodic table and we select the elements that we want. We mix them together and we heat them up and hope that we have an alloy that performs like we want it to. However, in comparison to baking a cake, making a new alloy is a little more difficult. We have to go to higher temperatures. It's harder to get the starting ingredients. They're not exactly on the shelf. And we have to make sure that everything plays well together. And it can be very difficult to make these alloys, and it takes much more time and energy, such that rather than all these great cake recipes that we currently have, often most of the alloys that we have are primarily one ingredient or maybe two ingredients. So we have our iron-based alloys, our aluminum alloys, our titanium alloys, which is kind of like having a cake that's 70% flour or 90% eggs. And so there's many other combinations of these elements that we have yet to be able to explore. And part of that is because they're difficult to make. And even once you make them, you have to go through the process of characterizing them. And rather than just a cake where you can take a bite into it, most alloys you can't get useful information out of that way. We have to instead section them, and we have to polish them, look at them under the microscope, and it takes much more time. And so this is one of the reasons why I'm interested in accelerating the search for different alloys using, in this case, parallelized electric field-assisted sintering. So this is one of the techniques that we use to make alloys. Electric field-assisted sintering is basically where we smush some metal powders between two punches, and we heat them with electricity and pressure. And doing that, we can consolidate our mixture of powders and to make an alloy. And this is good. We can make an alloy. It's faster in some cases than melting it, but it still is relatively slow. And so one of the things that I've been working on is developing a new methodology and some custom tooling that allows us to make many different little cakes at once. In this case, cupcakes. So what we can do is we can take in our cupcake tin and put different combinations of metal powders in each of them and heat them up and consolidate them all at the same time. Now, much like cakes of different compositions will rise at different rates, these alloys will densify at different rates. And so we can't just have a mated set of tooling that pushes on them all evenly, because some of them won't want to push yet and others will need to go much further. And so instead what we do is we put a filler material on top that can move around and apply pressure evenly to all of our little metallic cupcakes. And so at the end of the day, when we smush this all together and heat it up, we can produce these alloy arrays that now have almost 20 samples on them at a time. And so we already have a large factor of savings there on the synthesis, but now you also have all of your alloys on these nice convenient plates that you can then shuffle around to where you need to polish, to where you need to put them under the microscope. And in doing this, we're able to explore all those other combinations and hopefully find some alloys that perform better than what we currently have available. So next time you're experimenting in the kitchen, you can remind yourself that the folks at INL are doing the exact same thing in trying to develop the next generation of materials to power our clean energy future. Thank you.
Today is Elizabeth. She's a system integration engineer in integration and energy and market analysis in C170. Welcome, Elizabeth.
When we we imagine our green energy future, coal is often left out of the conversation. As a result, U.S. coal communities, which have been essential to energy production for over a century, are being left behind. But coal doesn't have to be a dirty word. In fact, it is essential to creating a secure, sustainable, and just energy future. So how can the green energy transition be achieved while supporting coal communities? We can repurpose current coal electrical infrastructure for nuclear power and convert coal into valuable fertilizers to reduce greenhouse gas emissions while supporting economic activity in coal communities. The first way to make coal sustainable is to stop using it to make electricity. Instead, 80% of existing coal power plant sites can be repurposed to host new nuclear power plants. This way, proud, resilient coal communities can continue to make an impact on our country's energy security. It takes twice as many people to operate a nuclear power plant as to operate a coal power plant. Both power plants share many of the same job functions. And some workers, like electrical and mechanical technicians, may transition directly between plants with on-the-job training. The transition would not only add new jobs to the power plant, but also indirect jobs to support the growing community in sectors like education and healthcare. Nuclear jobs bring tax revenue from increased wages to bolster schools and infrastructure, and eliminating greenhouse gas emissions can improve community health and quality of life. Nuclear can also help transition the coal mining industry into a greener future. With a nuclear power plant supplying heat and electricity, coal itself can be converted to hundreds of the different products we use every day, like cleaning supplies, plastics, adhesives, and most importantly, fertilizers. Creating fertilizers locally supports the agricultural industry and cuts down on costs and greenhouse gas emissions to transport fertilizers from far away. Even the waste products from this process can be beneficial to the community. Solid char from coal can be used as a soil additive to retain moisture and nutrients, improving local soil quality and reducing fertilizer runoff. Producing and using locally helps create smart, self-sufficient communities. Coal is no longer a dirty word in conversations surrounding green energy transitions. By reframing the way we think about coal, its uses, and its infrastructure, we can support strong coal communities while reducing greenhouse gas emissions.
Good job, everyone. So, right now we're going to let the judges take some time to collect their information and share that with me. And so while we're doing that, we'd like to invite you folks. We're gonna have a People's Choice Award. And so remember, I mentioned a little bit about the prizes that we have. And so our People's Choice Award, it's gonna be you voting for who you feel did a great job today. So if you have mobile iron on your device, if you click on this QR code, you should be able to put in your email address so we can make sure that we know who you are, and then you can select one of the people here to win our People's Choice Award. So if you have any questions about that, Lisa will be in the room so she can answer any questions. If your device isn't working, we have a laptop in the back where we'll have the website up, so you can actually go ahead and vote right here on the back, in the back of the room here on the left side. So, all right, so we're gonna take some time with the judges, and then we'll be back in a few minutes to announce our winners.
Again, thank you for our contestants taking time out of your busy schedules to come and do this, to our judges and to the audience. Wow, really awesome. It was really tough for our judges going through all of this, but we're really pleased with all of your participation and joining us in this. So the first award is going to go to the People's Choice. And so I would like to go ahead and invite Elizabeth up here to join me. So. Nice job. And how relevant. I mean, thinking about the coal pot, all the coal plants and the transition, so very relevant. And then I would like to go ahead and announce our runner-up, so number 2, who did a fantastic job. Kevin, come on up.
Thank you. I'm not gonna fill in the 8.
So go ahead and take those checks to the bank. All right, and then last but not least, I would like to go ahead and ask that Michael come on up. So great job. So thank you so much. And thank you all for joining us for our first ever SLAM.